Thanks, Chris, and thanks to the organizers for putting together such a nice program and allowing me to spend such a long time here. And thanks for you guys to showing up. So I prepared a talk. I was told to prepare an hour plus 30 minutes of questions, but I can adapt, so please ask questions throughout. And it's hard to prepare before you know exactly who will turn up. So if I'm boring you or I'm being too sketchy, just let me know and I'll change. Okay, so for this audience, I don't think I need to say why we care about defects, but I should tell you what defects I care about and why I care about those particular defects. Okay, so I'll be studying conformal and supersymmetric defects. So these are more complicated than the topological defects we've heard about, and so I can say less. But they're also constrained enough thanks to the supersymmetry that I can still say some things about these defects. So I can still get some exact results. And in particular, I will describe a relation between these defects and what mathematicians would call vertex operator algebras and what physicists call chiral algebras. So the left moving side of a two-dimensional CFT, just a meromorphic CFT or holomorphic CFT, whatever you want to call it. And because of complex analysis, then I can say something about these defects. So that's the idea. So I'll get some, out of 4 dimensions, I'll get something that's meromorphic. So what are the observables? What do I want to compute? Yeah, so in Durham, the boards are whiteboards, so they don't slip when you do this. But here they slip. So my plan of using the back one first is not so good. So the observables. So what I want to study are correlation functions or vacuum expectation values. In the presence of the defect. So I will put a single defect. Don't make me put more than one, that's too much for now. So just one defect. And then any number of local operators you want to insert. And you can also insert defect operators, so local operators that live inside the defect. Let me put a hat to highlight that. Okay, so these are the observables I want to compute. This is my defect or extended operator. And so in a CFT, you usually get to say, well, you get to say that one-point functions vanish because you don't have any scale, so there's nothing you can write for a one-point function. The only exception is, so in a normal CFT, in a CFT without a defect, you get to say that one-point functions are all 0 due to scale invariance, except the identity operator, which has dimension 0. Therefore, I can write this is equal to 1. Okay, now with the defect, this changes. And in this setup, I can write something. I have a distance to the defect. So now I can write an one-point function that depends on the distance to the defect. And there's some coefficient here that is, this is the dynamics of my theory. And then the power of this coefficient is just fixed by the scaling dimension of the operator. So that's just fixed by symmetry. Okay, so now when I say I want to compute correlation functions in the presence of the defect, I can no longer start saying that the 2-point functions are the first non-trivial pieces of data that appear. I need to go back to 1-point functions because now this can be non-zero. So now what I'll have then, this is my defect. If I have two bulk operators here, O1 and O2, I still have an OPE between them. I can still use the operator product expansion to replace this product by an infinite sum over all local operators with some coefficients. Plus non-scalars. So I just wrote this how a scalar appears for simplicity. So I still have the OPE, I still have these coefficients that I could compute without the defect, but now this is not enough to compute all correlation functions. I need to also know the 1-point functions, and then I will have new OPEs. And sorry if I'm boring you, but I will be looking at these OPEs in the Chiral algebra in a minute, so let me just at least set notation. So I have now a new OPE. If I have a bulk operator next to the defect, I can expand it in defect modes, and I can write a bulk operator as a sum with some coefficients of the defect in terms of defect operators. So I always put hats to denote things that live on the defect and no hats to denote things that live outside of the defect. And this depends on the distance to the defect, delta minus delta hat. Okay, and again, plus more, I'm just writing the first, how a scalar would contribute. And then on the defect itself, well, that looks like a CFT without a defect. So for defect operators, now there is no scale, so 1-point functions vanish, except the defect identity. One major difference is that there will be no stress tensor in the defect because it can exchange with the bulk. So the only stress tensor is the bulk one. So there is no stress tensor. But again, I have the OP in the defect. Okay, and now I can use the OP to compute any of these correlation functions. And I just need these pieces of data. I need, so I can compute any correlation function by knowing what I'll call the CFT data, which is the set of operators, the bulk OP coefficients, the defect OP coefficients, and the bulk to defect OP coefficients. And notice that one special operator here, defect operator, will be the identity operator, so that will be the 1-point function. So this is the same as the 1-point function of the bulk operator, so I'm hiding them in there. And if I have all of these, then I can compute all correlation functions. So that's what I'll be interested in. And of course, the set of operators, and this will be important in my talk, I'll want to organize them in representations of the conformal algebra, or if my bigger, in my case, the supersymmetric algebra. super conformal. Okay. You want to use crossing to be able, yeah, we could discuss what's the minimal set that I need using crossing, and yeah, I could probably do without, well, no, because if you just have a correlation function on the defect, forget about bulk operators, just put defect operators, I would need to compute. Well, you could try to use a bulk that decomposes in, yes, so that's interest, yeah. This is not necessarily a minimal set of data. If I have this, I have everything, but of course, and that's kind of the bootstrap idea that not any random set of these guys will do. And they are constrained by crossing relations, yes, indeed. Yeah. So I don't remember off the top of my head what's the minimal set. I don't know if it's easy to see it now. But yeah, there will be, you can, if you have enough, you are able to compute the rest, just demanding consistency, yes. Was that your point? Yeah. Okay, so now let me go to the series I care about. So what I'll want to study are, let me use the other board now. Or maybe this one goes up. And now I have the usual problem that half of the board is hidden. Yeah, it's not a boundary. Well, I mean, for dimensions, and I'll be studying surfaces, so you can actually go around them. So it's, yes, so it's not an interface, no. So let me go to that. And okay, all I said here was true, I guess, for any dimension of the defect. So it could have been a boundary, and then your theory ends there. An interface, I haven't talked about the other side, but for boundaries, this applies. What I'm about to say will be about theories where you can go around. But you can continue your question. Yeah, I guess if we had an interface, so if I was just thinking about a single theory, and I would allow a boundary there, but not an interface to a different theory, but then you'd have to say exactly the same. But I think you just, if the theory was on the other side, you just replicate it. You'd have bulk to boundary on the other side, and the two theories talk through the defect, and bulk coefficient on the other side. So that would be it. And then, of course, they satisfy non-trivial relations because of crossing symmetry. Yeah, so there will be two sets of coefficients. Yeah, I think there will be two different sets of B's, one for each side, and two different sets of lambdas, one for each side. And then they have to talk through the middle, so there will be some non-trivial intertwining of the two through. No, so the construction I'll describe to you requires enough supersymmetry. So I need to have an SL2/2 on a plane, which you have in 4D if you do n equals 2 or higher, in 6D if you do 2, 0. But you need to have this subalgebra because of the way I'll describe how I'll have to. I need the right R symmetry, basically, that I can twist with the SL2, the geometric one. So if you want to get a chiral algebra, it has to be You can do other twists, of course, that give you different things or topological things, but this construction needs this particular subalgebra of whatever your supersymmetry algebra is. And that's also how I'll be restraining myself to two-dimensional defects, because those are the ones that preserve the supersymmetries. Okay, any other questions? This was just a very generic introduction, maybe too generic for the audience I have. But now I'll be specific about the theory that I care about. So the theory. So I'll take 4D superconformal field theory with n equals 2 or higher supersymmetry. So this is kind of n equals 2 is in a sweet spot. It has enough supersymmetry to be tractable. It's a lower bound, but it's kind of richer and more things happen than if I put more SUSY. But of course, you can put more SUSY and it just comes along for the ride in all the construction I'll be describing. And by now, there's a very large zoo of these theories that are obtained with many different constructions, and they're strongly coupled, etc., which motivates me wanting to define the theory in this abstract way that saw a revival since the work of Eric Ratazzi, Richkov, and Vicky more than 10 years ago now, where you try to describe your conformal field theory abstractly in terms of what their correlation functions are instead of giving me a particular microscopic description. So I will be taking that approach. I will take that the CFT is defined by the set of all operators and their correlation functions. And I should say all operators here, but as I said in this talk, I will restrict myself to one defect only. But baby steps. And so the idea of this talk is to first fix the symmetries. So disentangle what is kinematical from what is dynamical. And after you fix everything that symmetries can fix, then you can try to obtain results for the dynamics of the theory, which in this case I will be focusing on a subsector of my SCFT that is described by a chiral algebra. So the plan will be, I will first introduce the defect and the theory. Then I will fix with symmetries. And then I will introduce the chiral algebras. And then I will finally describe the general properties of the chiral algebras when defects are present. So not any random chiral algebra will be arising from a four-dimensional theory. So there will be constraints on the chiral algebra that come from for the unitarity and the four-dimensional theory itself. Okay, so let me write my defect. I can push that up if I get that. Okay, so let me start with sorry, I made a mistake here because I did not flip the page. I do not start with 2, I start with 1. That makes more sense. But anyway, 1 is short. So maybe since it's a small audience, how many people have seen for the n equals 2 series before? It's okay if not, because I have assumed the most general audience possible. Okay, so I'll try to make everyone happy and probably make no one happy in the end, but let me say what they are. So I'm interested in for the n equals 2 SEFTs. These are invariant under, so the symmetry algebra is SU2, 2 / 2 in Lorentzian, which has as a maximal subalgebra SO4, 2. That's just a conformal algebra. And then it has an R symmetry that will play a very important role. So it has an SU2 and a U1 R. And so the conformal algebra in 4D is generated by momentum, the special conformal transformations, rotations or Lorentz transformations, and dilatations. Then I have 8 supercharges. That I'm going to call Qi alpha and Q tilde I alpha dot. So this I is 1 to 2. This is why I have n equals 2. And these guys, they are rotated. This is an SU2R doublet. So these are symmetries, part of the superconformal algebra in conformal field theory. And they rotate my supercharges. And then I also have the conformal supercharges. Just like when you have momentas in a conformal field theory, you also have special conformal that you can think as an inversion followed by a translation followed by an inversion. So you conjugate by inversion to go from P to K. And similarly here, if you do this for the supercharges, you get the conformal supercharges. The conformal supercharges. Let me call them S and S tilde. And so these plus the SU2R generators and D1R, these generate my full algebra. And I will want to organize my operators in representations of this algebra. So I will organize the operators in multiplets that look somehow like this. So I have a conformal primary that can be related to other conformal primaries by the actions of the supercharges. And you can act with all the supercharges as long as they don't kill your state, and you get some big superconformal multiplet. And then I will then label my operators by their scaling dimension, their spin, how they transform under SU2R, and so their SU2 representation, their R charge, and any other flavor symmetries they have. Okay, so this was a quick crash course if you haven't seen n equals 2, if there are any questions. So now what's the defect I want to put in it? No, up and down. So I'm going to put a flat defect. I want to preserve as much symmetry as I can to preserve the chiral algebra that I'll describe in a second. So I'm going to put a flat defect. That's a two-dimensional surface, and that it preserves still some supersymmetry. So inside 4D, I'll put this 2D defect that preserves inside it a 2,2 conformal, superconformal algebra. Okay, so on the defect I have this 2,2, and so the symmetry is broken to SU1, 1/1, SU1, 1/1. So this is just the n equals 2,2 superconformal algebra on the defect. There's the left and the right moving bit on the defect. And then there's this, which from the defect, it looks like a global symmetry. It's not part of the superconformal algebra. And this C, so this is a global symmetry for the defect. And C is a combination of two U1s. One is M, which is the rotations around the defect. So you can go around this defect because it's a surface in 4 dimensions, so you have one more dimension to go around. And the other is the cartan of SU2R. Okay, so the defect from these two generators in this particular combination, from the defect point of view, it just looks like a global symmetry. And then the others that are preserved are inside the superconformal algebra. Okay. So well, yes, actually, M and R are preserved separately. So the 3 U1s I had, M, which is what people usually call orthogonal rotations. If you just have a defect with no SUSY, you tend to want to study defects that study those, that preserve those. So in this case, both M, R, and little r are preserved. But then if you want to see how they organize themselves in this algebra, you find that the opposite combination is inside there. And so is the U1R. And what's left over that is still preserved is this particular combination. So this is just a matter of embedding this superconformal algebra in that one. And that's what you find. But yeah, actually all the U1s are preserved in this story. Is this synthetic rigid? I think it's rigid. So yeah, you just start from what is preserved. And okay, you of course break translations, so you don't care so much about things that end up being in these translations, and what is left over, if you want to preserve the amount of supersymmetry, and I think it ends up giving you this. So even like the weights of this, the relative weight, yeah. Yeah, I think that comes out. That's what, because it's really the plus and the minus combination. The minus combination is something like J minus J bar, if I'm remembering, because these guys have an R symmetry, and it's a U1 R symmetry, and it's a combination of the two. So I think this just comes out. I don't think you have any wiggle room to. Yes, so I'm gonna, thank you, yes. We broke a lot of symmetries, so every time we break a symmetry, we generate, we modify word identities, therefore we have to generate defect operators. And that will come in a minute. Thank you. And that's indeed where I want now to go into kinematics. So we broke some symmetries, and as Chris alluded to, this will give me some guaranteed protected operators in the defect. So as we heard in Giuseppe's talk, one obvious guy that appears is the minute you break translations in the direction orthogonal to the defect, which I cannot avoid doing, the stress tensor is no longer conserved in the directions orthogonal to the defect. So the conservation of the stress tensor, if nu is orthogonal to the defect, gets modified with a delta function that has support on the defect and a defect operator that is called the displacement. It's called the displacement because you could try to integrate it to translate the defect to displace the defect, which is related to the fact that it's related to broken translations in directions orthogonal to the defect. So this guy is there. But now, of course, I have some supersymmetry left, and I also broke some supersymmetry. So I broke translations. I broke some SUSY. So I'll be able to write a similar non-conservation equation for some of the supersymmetry currents. And I get some defect operators. Let me call them lambda and lambda tilde. And I also broke the R symmetry, the SU2R. I broke it down to the cartons. Only the cartons are preserved. So after this bad management here, so I broke SU2R down to U1R. And so I get the lack of conservation of the two currents from here will give me another defect operator. So here are your, I think this is what people now call tilt, the one that, well, this is an R symmetry, not a flavor symmetry. But okay, I broke the R symmetry and I get two guys. Okay, and I broke two translations, so I get two guys here. And I wrote them in this suggestive way because they are actually all related by the preserved supersymmetries. Okay, so if I want to call here on the defects, let me call them G plus minus and G bar plus minus, as is normal in the 2D CFT literature. These are the supercharges on the left moving side and on the right moving side. This whole combination actually forms two, not one, but two n equals 2, 2 supermultiplet that are chiral, antichiral, and an antichiral-chiral pair. So chiral, antichiral means that the superprimary, this guy here, is killed by G plus and G bar minus. And if I want to draw this one here, then I get to act with G minus and with G bar plus. And I get this multiplet. And if I do the other one, the antichiral-chiral, it will be killed by G minus and G bar plus. And so here you get the same multiplet, but with acting with G bar minus. Well, a similar looking multiplet, not the same. There are two of these O hat tilde, which you can count by the fact that I broke like the J plus, J up and J down, J plus and J minus, the raising and lowering ones. and one will fit in a chiral, the other in an antichiral as the superconformal primary. Then I broke enough SUSY that I can populate two of them. And then you expect two displacements because I broke two translations, and one will fit in one in the other. And they are related by this symmetry. And the displacement is then the top component, which means that it's killed by all preserved supercharges. It's at the bottom of the multiplet, which funnily is called the top, but that was not my doing. Yes, I forget if there will be the difference and the sum. One will give you a little r, and the other one will give you this with the minus. I can be more precise if you want, but I actually didn't write it here. Any other questions? Okay, so these are the defects I want to study. And as Chris was saying, just because we broke some symmetries, we know that these operators are there. Their dimensions are actually fixed by these word identities, because I know the dimension of the stress tensor, I know the dimension of a delta function supported on the defect. So this guy has scaling dimension equals 3, and then the other ones similarly. And because this operator was defined by this word identity, I don't get to redefine it. So its normalization was set when I wrote this equation. So where usually we like to go to orthonormal bases and make everything 1, but we cannot make two-point functions 1 here, and that's the displacement two-point function that Giuseppe talked about on Tuesday. So these guys, the two-point functions of all of these guys, will be physical, and it's something we would like to compute, and I will tell you how we can compute them from chiral algebra in a little bit. Okay, so the two-point function of the displacement and the others are physical. They're just not my choice of normalization. And we typically call this guy CD. I just put a hat to mean the coordinates along the defect, and this is just fixed by the dimension of the operator, which is also protected by the word identity. And similarly, I have the two-point function O, etc., etc. Now, as you can imagine, because these are related by supersymmetry, these are actually all related to each other. So there's no new information in one versus the other. And moreover, remember in the beginning I was talking about one-point functions. We also have, in the presence of the defect, the stress tensor will acquire a one-point function, and its coefficient I'm going to call AT. And in a generic CFT, this piece of CFT data and that piece of CFT data are unrelated. They're just two ways of two things. But if you have enough supersymmetry, they actually turn out to be related. So we showed that for surface defects, so surface I mean 2D, in 4D with n equals 1 or higher supersymmetry, so I didn't even need as much as I used. These two guys are related. And you can show this basically using the preserved supersymmetry plus the word identities I was writing for the broken ones. So the broken symmetries still buy you something because they relate bulk and defect integrated correlators. So plus word identities from broken symmetries. And in this paper, we wrote also a proposal for different dimensions and different codimensions. And I believe Costas Bacaz already gave a talk where they've now proven this result, what we proposed for basically any supersymmetric defect. So there's now a proposal of a proven relation for supersymmetric defects. That was his work with Lorenzo Bianchi. So what this means is that in my setting again, any correlation function involving operators in the displacement supermultiplet with itself, whatever pair you pick there, in the stress tensor supermultiplet, because this guy in an n equals 2 theory is also a top component of a big multiplet, so there's a bunch of guys in there with the displacement. And the one-point function of anyone in the stress tensor supermultiplet. These are all fixed from AT. And the relation is that CD is minus 12 AT, which is a meaningless until I tell you what kinematics I put there, but there is a relation. And because CD is the norm of an operator, it has to be positive in a unitary theory. So this has to be positive, and AT will be negative. So this is norm of the displacement is positive. Okay. So now now that I fixed all the kinematics, this is all I needed, I will tell you how the chiral algebra comes about. Are there any questions while I erase? Yeah, so those end up giving you the Hoffmann-Malda-Senna bounds, right? Relating A and C. You mean now you want to get something on AT? Yeah, there's also probably some, yes, there, I guess, yeah. I don't remember. It rings a bell, so maybe I've seen it, but I don't remember. Yeah, we can talk later. I'll probably refresh myself with, yeah. So I'm emphasizing this for reasons that will become clear in a minute, because this will basically give me negative dimension operators in the chiral algebra. That's why I was emphasizing this particular relation. Okay, so now I will recap the chiral algebra, or explain the chiral algebra first without defect, and then I'll put the defect in to add too much. So chiral algebras of n greater than 2 SCFTs. And this was work with Chris Beam, Pedro Liendo, Wolfgang Pillars, Leonardo Rastelli, and Baltvanres. And the claim is that there is a subsector of local operators. I'll put defects in a minute. In any CFT with n equals 2 or more supersymmetry that is isomorphic to a two-dimensional chiral algebra. Isomorph. So the claim is the following. Let me take for concrete, I'll take a plane. For concreteness, I'll take the 3-4 plane. I'm drawing the plane here, but there's nothing on this plane. There's no defect yet. This is just, I'm choosing a plane inside R4. And I'll put complex coordinates. And now the claim is that there's a subsector of operators. So there's some peculiar operators in the 4-dimensional theory that if I restrict them to the plane, so they depend only on z and z bar because I chose to put them in the plane. If I now compute their correlation function, I get something that is meromorphic. I get the correlator of a meromorphic CFT or a chiral algebra. Okay, and in more detail, what are these guys? And this is where the amount of supersymmetry I have will be important. So I'll be wanting to study the correlation function of some 4D operators on the plane that transform non-trivially under SU2R. So they will carry some SU2R index that I'm writing schematically as I. So this is in a non-trivial SU2R wrap. They must transform all of them. And then I'm going to do something even more funny, which is it's not these guys that actually work. I'm going to contract this SU2R index with some vector that depends on z bar. Okay, so I'm doing some sort of twisted translations, as I'll explain in a minute. So if I do this funny business of contracting the SU2R with some vector that depends on z bar of the operator, and I sum over this, this is what gives me my F. Okay, so the z bar dependence drops out after I do this, and I get a chiral algebra correlator. And what do these guys look like? So these funny operators that I'm taking, because it's this combination that becomes just dependent on z, these are something like the highest weight of SU2R at the origin. Sorry, no, I'm at z bar. Plus z bar, and then the lowering operator in SU2 on the highest weight. So I start with the highest weight, and then I'm adding all the others until I get to the lowest weight, and I'm adding them with z bar dependent coefficients. Okay, so plus until I get to the lowest weight. So if I go to the origin, I just have the highest weight of SU2R, But as I translate away from the origin, I start picking up all the other components, and that's how my correlation functions will end up being non-trivial. Because if I just had the highest weight, everything would be 0. Okay, so now why? No, so what I'm about to tell you is that why this happens is because I'm passing to a cohomology of a given nilpointed supercharge. And so I'll want operators that are in that cohomology. And in particular, they will have to transform non-trivially under SU2R to be in cohomology. So it's a restricted set of operators from the superconformal multiplets. Some superconformal multiples will have one operator in cohomology, and some will just not be in it. And at most, they have one if you just have n equals 2. So you use up all your supersymmetry in the construction, and the chiral algebra you get is non-supersymmetric. So I cannot, what I learn through this is about some correlation functions, well, about some piece of the correlation functions of certain special operators. And actually, work of Hugh Osborne and Francis Dolan, they were looking at 4-point functions of some BPS operators, and they were finding inside the generic 4-point function, which looked complicated, there was a function that depended only on Z, and it's this one. They were solving word identities for the supersymmetry and fixing the form of the correlation functions, and they kind of stumbled upon this but didn't realize what it was. So why is that this subsector is the cohomology of a supercharge that I'm going to call square Q. That is a combination of a normal supercharge and a Poincare supercharge. So you see I'm breaking things and I'm adding different components of SU2R, so I'm completely destroying my SU2R with this. Well, not completely, but it's gone. And cohomology, so I'm looking at operators then that are closed, but not exact. Okay, and in this, and the Z bar dependence is Q exact. And so it drops out. So let me put a bit more word in this. In that plane, where I have my chiral algebra, I have two global, well, I have the global conformal transformations, which are the left and the right. So I have two SL2s. Which I'll even write explicitly, so it's less vague. So this is an SL2. And then I also have the SL2 bar. And this is an SL2 bar. Okay. So now this one, all of these guys, they actually commute with this funny supercharge. So if I find the cohomology at the origin and I move them in the Z direction, they remain in cohomology because they commute. Now, from what I've been telling you, what I would like is that this guy is Q exact, but this does not happen. So this is not Q exact, but I can define an SL2 hat that is given by these hatted operators. And sorry, this has nothing to do with the defect. This choice was made before defects were introduced, but these are just still on the Chiral algebra planes. There's no defect yet. And these guys are just the barred ones plus the lowering SU2R generator, the raising one, and the Cartan. And this SL2 hat, which is basically the diagonal of SL2 bar and SU2R, this is Q exact. Okay, so now you see what I had to be doing there. I cannot just simply translate operators into Z bar direction. They would not remain in cohomology, and the Z bar dependence would not be Q exact. But if I do these twisted translations, then I get something that is that doesn't see the Z bar. Okay, so if I find the cohomology at the origin, and I'll show you in a minute that it's non-trivial. So there's a non-trivial cohomology at the origin. It will be some list of operators that transforms under SU2R. Then I can define my Chiral algebra operators that depend only on Z as the cohomology classes of these guys, which are, so I want to start from the guy at the origin, which will turn out to be highest weights of SU2R. So this is at the origin. I start with the operators that are in cohomology at the origin. I can freely translate in Z because it commutes with the Q. And I can translate in Z bar if I use the twisted translations, the hatted operators. Okay. Okay, so these twisted translations are precisely what I wrote here. So that would just come out if you just stumble upon this correlation function in this procedure, you'd get something meromorphic, and the thing you'd have built was precisely these twisted translations where you see that away from the origin there's the action of the lowering operators because I'm translating with this guy here. Okay, are there any questions? L-1 bar. Yes, thank you. It's the, yeah. Yeah, so this was just to be very concrete, but any other questions? Okay, so now, do I get something interesting or not? It's my choice. It's my choice. No, I'm. Yeah, it's my choice of the. I mean, I have this SL2, right? Now this is what I have on the plane. Yeah, I guess I pick an origin and I look at my operators there, and then wherever I pick the origin to move it away from that, I guess different choices should be equivalent. Just like I picked the plane and my choice of plane ended up picking what supercharge I used, but there's nothing special about 3-4. I could have picked any other plane and you would have gotten a different supercharge. So yeah, I think it's just my choice. I mean, I'm always picking an origin when I'm talking about, you know, a conformal primary. It's annihilated at the origin that I picked, right? So that's, I picked the origin then when I was defining my operators. And if you wanted to do radial quantization about a different point, you can. You just, I think that's, well, we can talk more, but I think that's just my choice. So now if you look, because you have the supercharge, so you can just try to compute what operators can be in this cohomology, or are in the cohomology. You find a list. Okay, so at the origin, the cohomology is non-trivial. And I get operators in certain short representations that satisfy these two conditions, that their scaling dimension is twice their SU2R charge plus the Lorentz spins. And then the U1R charge is the difference. Okay, so these are called Schur operators because these particular conditions had been found before. They are the operators that contribute to the so-called Schur limit of the superconformal index. So if you're familiar with that, these are exactly the operators I'm finding. But if not, I've just found a condition that the operators must obey. And now I'll introduce defects in a minute. The last thing I want to say is that there's a particularly interesting operator in this cohomology. That's the SU2R current. So the SU2R current satisfies this. It sits in the same superconformal multiplet as the stress tensor, which does not satisfy it because it's a scalar under SU2R, a singlet. But this guy will play the role of the stress tensor. And after doing this procedure, I will get something that I'm already calling T of Z, which is the twisted translations of the SU2R current. So this guy is the SU2R current. And in cohomology, it gives me something that I'm calling T of Z because it is a stress tensor. It has the OP of the stress tensor, which you can, because it is an R symmetry current, you can fix some terms in its OP from R symmetry. And then you can do this whole twisting, and you find the OP between two stress tensors in chiral algebra. So while before I only had global part of the conformal algebra in the plane, I just had an SL2, I didn't have full Virasoro. Because I get this stress tensor, the SL2 becomes the Virasoro symmetry. So there's an enhancement of the geometric SL2 to full Virasoro. And now I can compute the two-point function of this guy, which we know in 2D should be this. But I can fix it from 4D. And I get this relation that the central charge of this Virasoro algebra, C to D, is minus 12, the 4-dimensional central charge. And by 4-dimensional central charge, I just mean the 2-point function of the stress tensor in 4D. Okay, so the 4-dimensional central charge is a 2-point function. Again, it should be positive. So this means that the chiral algebras that come from 4D n equals 2 series are necessarily non-unitary. They're non-unitary in this very specific way. Some operators get a negative norm. Yeah.
Something that the spin 1 in the bulk extensor, the spin 2 on the surface.
Yeah. So, well, I'm taking the plus plus dot component, right? So that's, you have to think about that, right? So in the plane, you have, so it will always be the highest weights under Lorentz that become in chiral algebra. That also follows from these equations that I wrote here for you to be able to satisfy this. So these are the guys that appear. So this becomes the, yeah, I mean, it has dimension 2, right? I just have a chiral algebra, and of course it has h bar equals 0, but all my operators have h bar equals 0. All my operators are conserved currents, basically, if you're thinking about the chiral algebra.
But does it transform the right way into the bulk
It transforms the right way under these guys, which is what I have left, right? I mean, it has 0 L hat, right? Because it's in cohomology. So it has 0 L hat 0. And it transforms the right way in this. There's a slightly subtle point, which might be where you're alluding to, which is if I do a mode expansion of this guy, I'll get some modes. And I have to show you that these modes match the global ones for 0, plus and minus 1. This was never fully shown. Okay, we checked in a few cases. We tried to argue, but in the original paper, we never managed to show that these modes completely match that. You can show it for some operators, so you'll have to look at how the OP between T and other operators, and in some cases, you can show that they're the same. But so there are a priori. Now I've introduced the Virasoro structure with Virasoro modes, but L-1 didn't have to act geometrically. And that's what I'm claiming it does. This guy is, well, yeah, but all at the same point with some z-bar coefficients, yes. Well, z-bar completely drops out because it's Q-exact. So in cohomology, the guys I get at the very end are local in the chiral algebra. Any other questions? Okay, so the chiral algebra is non-unitary. Some operators get negative norms, and actually you can get a lot of mileage by trying to think which ones do and which ones don't, and constrain chiral algebras in this way. But you still have that local operators. If I take another operator in cohomology, it will have some OPE that has the usual scaling weight term here. And this weight is still positive. So I'm still getting positive dimension in chiral algebra. It's just some negative norms. These will change once I put the defect in. Okay? So very quickly, maybe I can do an example that maybe will help. Recover the eraser. So the simplest example is perhaps the free hyper. So the free hypermultiplet are two complex scalars. Q and Q tilde. And I can organize them in doublets of SU2R like this. Okay, and these are just complex scalars. And then if I want to check the 2D OP, for example, let me take Q of Z with Q tilde of 0. So Q of Z will be this twisted translation. So it's Q of Z, Z bar plus Z bar. This is the highest weight, and the lowest weight is that guy. So actually minus Z bar Q tilde star. Okay, and the other one I took it at the origin, so Q tilde of Z at the origin is just the highest weight. And so if I take the OP between these two guys, I get, well, Q1 Q tilde gives me 0. And then I get minus Z bar Q tilde star with Q tilde. And that's non-zero. And it will be 1 over minus Z bar over Z bar. And so this just cancels. Okay, so I get my, this looks like a beta gamma system. It's a pair of symplectic bosons. They're scalars, so they commute, yet they have H equals a half, as you can read off from the dimension, but that's my non-unitarity at play. So I can get commuting half-integer dimensional guys, and they also have, you can also compute C to D, and it's -1. Okay. And then you can look at more complicated examples. And for example, the simplest Argyres-Douglas theory gives you the Liang minimal model. Yeah, if I had computed actually something else, maybe I wouldn't. Yeah, that was from my choice of of SU2R, my SU2R conventions, and where I put that minus sign. And oh, sorry, and it's another example of my norms don't have to be positive, right? So you can actually show, and it has to do precisely with SU2R, that you could have predicted this sign from 4D. Predicted this sign from 4D. So in 4 dimensions, of course, norms are positive. So norms of all of these guys are positive. Because of this SU2R business, these twisted translations, I get something that has negative norm. I mean, you could, but then you need to ask what's the, So there are two different norms. There's the four-dimensional norm, and the four-dimensional norm obviously is positive, and that's the one that you know, like the stars I've been putting. And then in chiral algebra, you could be using the standard norm in radial quantization, and that's what you would get. And then if you want to put i's in front of your operators, you can do that too. But then the dagger of that will get a minus. So there are two different norms. The four-dimensional norm is not related to the two-dimensional norm in an obvious way. Well, it's not related. It's something else. And well, you can see how you get the two-dimensional norm because it has to do with I don't have it anymore. Well, you're picking up the lowest weight from the twisted translations because that's what will be non-zero. And there will be some signs that appear. And that's an interesting thing. My recent work was precisely on, with Chris, Leonardo, and Arash, was on seeing what conditions come from that. So that you already saw an example in the stress tensor, but you see another one here. And this basically has to do with the art symmetry representation of the guys. You could predict. Of course, you have to be careful in normalizations. Yes, I can stick a normalization in here. In fact, for the stress tensor, I have to stick some normalization in front to get the canonical OP, but then I need to remember who's conjugate of whom, and then you don't get it. Any other questions before I add defects? So now I'm going to add a single surface defect that's n equals 2,2, so the ones I had introduced, if you remember, a bit ago. And sorry, maybe it's easier this way. I'm going to put it orthogonal to the chiral algebra plane, such that it pierces the chiral algebra plane at a point. And so from the chiral algebra, it will look local. It will be at a point. But it's, of course, a defect. And then we'll see what comes out. OK. So I finally add defects. So this is my chiral algebra plane, still no defects. So this is x3, x4. And then I want to add a defect that's orthogonal to the plane, and it pierces it at a point. So this is a 2D n equals 2,2 defect, the one that I just described. Yeah, I put it this way to preserve the supercharge I wanted. Yeah. I would break the right, because I need to preserve precisely the supercharge that I used, this funny Q that had a combination of supercharges. And to preserve it, I need to pick this supersymmetry in this configuration. OK, and now I can keep my bulk operators on the plane. So sorry, I should have said, I said it in the answer. This preserves my supercharge. And so it was shown, well, that was shown by Wim Pellers and Rastelli, and Gayotto Cordovan showed that this particular configuration preserves a supercharge. And then they showed, looking at the index, that it should introduce a module over the chiral algebra. And now what we wanted to do was take this construction and actually look at the OPs and see what I can tell you about the behavior of that operator in chiral algebra, how do I identify it, what its OPs are, and so on. So before we had a non-unitary chiral algebra, but in a very mild way. All operators had, all of these guys have positive dimension in chiral algebra. A few acquired a negative norm. It's actually under more control than I can tell you which ones should acquire negative norm. But what happens now when I put this guy there? What are its properties? So that's the question we wanted to answer. And notice that because what I've done, the defect also will intersect the chiral algebra plane at infinity. So if I'm computing correlation functions, when I pass to the chiral algebra, I will see an insertion here and an insertion at infinity. And then I am free to add operators, defect operators, provided they are exactly at that point. So I can add one defect operator here, and I could also add one at infinity if I wanted. I just have to find which operators are now, which defect operators are now in cohomology.
Is there like a conformal transformation of this where I could just like get the sphere?
Probably, then I would probably want to worry about any anomalies in this, and it would make my life much harder. Or maybe, yeah, at least I think it would make my life a bit harder. So I prefer to keep it flat and just have an insertion at infinity.
Previous story where you did everything on the plane, can you do it on the sphere too?
Yeah, then there are some papers with relating it to the omega deformation, that there is more natural to put things on non-flat surfaces, etc. But yeah, so there's more there. But I can define everything with flat defects. But yeah, you could do that if you wanted. Any other questions? So I'll just, so it gets, as you'll see, the non-unitarity gets a bit nastier in this case, but I'll sketch for you what we get. So now I can compute correlation functions in chiral algebra of this configuration, and you can ask what defect operators are in cohomology. So just the defect itself, it preserves the supercharges, so it's there. Or if you want to say the defect identity is in cohomology. But it could be trivial. I will show you it's not. But yeah, it could be trivial. I will show you that. Well, I'll come to that in a second. Remind me if I don't. But what other defect operators obey those conditions that I've erased? And these turn out to be anti-chiral defect operators. So just like I had introduced previously, so for example, the displacement supermultiplet contributes. It's not the defect, the displacement itself, it's the superprimary. So it's the one I was following O hat, the one that comes from broken SU2R. Obviously, the defect identity. It's a bit trivial. And then you can also have some marginal defect deformations that are anti-chiral. And you'll be able to see them in chiral algebra. OK, and so note that I'm just inserting one defect, and I will not attempt to translate it from the origin. That would be something interesting, but I won't. I haven't done that yet. I don't even know how to do that. So now, to answer Giuseppe's question, is the defect identity trivial? What can I tell you about that? So let me start by giving it a name. Let me call sigma the defect identity in cohomology. And now you can ask, what's its dimension? And this will immediately answer your question if it's trivial or not. So what's its dimension? I should look at its OPE with the stress tensor, which will be something, and then there's the pole. And these somethings I will fix later, but let me start just focusing on this term. So to extract that term in chiral algebra, I would compute this correlation function, which will give me h sigma over z squared. But if you look at the picture, the defect at infinity is already there, the defect at the origin. And I told you T came from the SU2R current. So this is nothing but the one-point function in the presence of the defect of the SU2R current. Which I could relate using SUSY to the one-point function of the stress tensor, which is AT. Right, so the one-point function of the stress tensor by SUSY is related to the one-point function of the SU2R current. The SU2R current, I've shown you, it's the guy that gives me the stress tensor, T of Z in chiral algebra. And to put it in the presence of the defect, I have to compute this correlator, because there's a defect at infinity and at the other, it's the same defect, but it touches at 2 points. So you can compute this, and you get that H sigma is 3 pi squared AT over 4. So it's non-trivial. And it has negative dimension. So now things get a bit nastier. OK. Then you can proceed and use four-dimensional unitarity and four-dimensional selection rules to try to constrain also these guys. And you actually find that this is 0. So the effect introduces an operator that's a Virasoro primary. That's still very nice. However, you also find that there could be more there. And L0 could have a non-diagonal action if you have defect marginal operators. These ones of the anti-chiral type. So they are allowed by four-dimensional rules, selection rules, to appear in chiral algebra. So you should start getting log modules. And then the 1 over Z pole is the chiral algebra avatar of the displacement supermultiplet. So you get this guy. So this would be what you would think of L minus 1 on the defect. That's the derivative on the defect, and you get an avatar of the displacement, which kind of makes sense that you would get that one, since the displacement would translate the defect. OK. Yeah. So this is what I would call derivative of sigma. But if you start from 4 dimensions and you look at the selection rules, you see that the operator that can appear as the 1 over Z pole is this one only. So that's, you make this identification. Yeah. Provided, again, you can identify L minus 1 with L. But yes. The conformal weight works out in chiral algebra, yes. And you can compute some of these correlation functions because we had fixed them by supersymmetry. So you can compute stuff like this. This is the 2-point function between the displacement supermultiplet and the stress tensor supermultiplet in the presence of the defect, and that's how we fix this type of stuff. It's because we can compute them. Yeah. And from this, well, yeah, the dimension works out. Well, it's our proposal that the dimension works out. We have a proposal for what the dimension of defect operators should be in chiral algebra. And it's such that this works out, and it's also what's needed for the superconformal index to work out, etc. But it's still, that's what we propose. This guy has dimension in chiral algebra. You would have to do, I think, you would have to compute this to confirm that, and we haven't done that. We have a prediction from this, from chiral algebra, if everything goes through. OK, so this is what I wanted to tell you. You can, of course, look at more. You can try to establish properties of this sigma, the defect identity, by looking at its other OPs, and then you can start putting non-trivial operators there. This is still very nice, even though you can have a non-diagonal action. If you look at other defect operator insertions, you can get all sorts of weird modules. You can get dimensions unbounded from below that appears even in the defect in the free hyper. So the story gets much richer. The representation theory in mass gets much richer because you have all of these funny modules. But the defect identity still remains quite nice. It just has negative dimension. OK, thank you very much. That's where I'll stop.